Hi, let's talk about solutions in chemistry. When we're dealing with solutions, typically we talk about their concentration in terms of molarity. There are occasions that we use percentages, mass volume or volume percentages, or parts per million. There's also some other units, but overwhelmingly we use molarity. You've seen it on reagent bottles in the lab. It's just all over the place. All right, so important to note, molarity is defined as moles of solute per liters of solution. The solute is whichever component of your mixture is in lower proportion. Typically, it's pretty obvious. If we have 0.1 molar sodium chloride, it means you've got 0.1 moles of sodium per liter of solution. A liter of water is about 50 liters, so you got 0.1 liters or other moles rather of a solute versus tens of moles of solutions. Anyway, just like when we have other terms in word problems that have kind of casual units like percentages, it's very important and useful to rewrite the units of molarity into something that is useful to us. As it stands, we typically see something listed as M. So down here I say 0.15 M calcium chloride. We want to turn that M into something that lets us do dimensional analysis. So let's just jump into a problem here. As I look at this one, how many grams of calcium chloride are in 400 mils of 0.15 molar calcium chloride? The two things that I want to do, always be in the habit until you're really comfortable with this, of rewriting that. And this will mean 0.150 mole of calcium chloride per liter of the solution. I like to abbreviate solution as this SOLN. And the other thing we need to do is eventually we want a mass, so let's just work out what the molar mass of that guy is. And calcium is 40 grams per mole, chlorine is 35.45, so taken together this is 110.9 grams per mole. All right, if we pause for a sec and look at what we have in front of us, we're asked for grams, so I've got grams listed there. That's going to come from moles. I've got moles as part of the concentration. So that's taken care of. And the rest of it's all just about the volume of the solution. It's given in mils, but the mils to liters is fairly straightforward. All right, these lend themselves very well to the roadmaps that I like to push. So the roadmap here would be mils of the solution going to liters of the solution. From liters, we use the molarity to give us the moles of the solute, which in this case is the calcium chloride, and then the formula mass or molar mass to get the grams of calcium chloride. Okay, so if we've never seen these problems before, it's a little bit of a treasure hunt of trying to follow through the units. But once we've done a couple of them, we sort of see this pattern of going from a volume, using the molarity to come up with the number of moles. Maybe we end there, we do some sort of chemical reaction there, or maybe we press on and report an answer in grams. Okay, solution then, just plug in the numbers into our roadmap. I started with 400 mils of solution. If I have all the space in the world, I might write that out as 400 mils of calcium chloride solution, but I find I run out of space more often than not. All right, converting that number of mils into liters, I have 1,000 mils is 1 liter. We can now use the molarity, and that is that 1 liter of the solution is 0.150 moles of calcium chloride. And I want this answer expressed in grams. So I have that 1 mole of the calcium chloride is the 110.9 grams. Checking my units, my mils cancel, my liters cancel, my moles cancel, and I'm left with then grams of calcium chloride. run off the page one more time. And then punching the buttons in the calculator, this works out to be 66.5. That, in a practical sense, strikes me as a little bit high. I don't know how soluble calcium chloride really is, but it's a made-up problem, and that would be the numeric answer for it. All right. Next problem, a little notch tougher. If we have 25 mils of one solution, a sodium hydroxide solution, and we're allowing that to react with sulfuric acid, and it takes 25 mils of this solution to react completely with 30 mils of the other one, we want to find out the concentration of that second solution. So a couple things to do here. One of them is going to be very clear what it is we're trying to find. So, and I think it's a good strategy to write that out sometimes. Find the concentration of the sulfuric acid, and really what we want to be sure we've got is what that means, and that's going to be moles of the sulfuric acid, the H2SO4, per volume or per liter of H2SO4 solution. Okay, we're given the volume, that's the 30 mils, so this denominator is pretty much taken care of for us. So what we're really trying to do is find the moles here, and that's not dissimilar from the problem above. We've got a volume of sodium hydroxide and its concentration. That'll tell us the moles. We'll have to write out a balanced chemical reaction that'll let us go from moles of the sodium hydroxide to moles of the sulfuric acid, and then when we divide by the volume of the sulfuric acid, we'll have this ratio, which is the molarity. Okay, we need a chemical reaction here. This is an example of an acid-base neutralization reaction. They're pretty common, so it's a good one to recognize. And that is that the sodium hydroxide reacts with sulfuric acid to give us sodium sulfate plus water. These reactions, again, are fairly common. When we see this leading hydrogen, that's going to be an acidic proton. We see this, or we hear its name, sodium hydroxide. We want to be thinking, hey, that reaction is H plus OH minus gives H2O. Okay, so since I have two protons here, that means that I must need two sodium hydroxides. Don't really care about the rest of it, but that gives me two waters there. So what's important is that I've got two sodium hydroxides for every one sulfuric acid. Okay, a roadmap for this is going to be that I'll start with the milliliters of sodium hydroxide. And the previous problem, I turned milliliters into liters so that the units matched up with what's on molarity. It is not always necessary to do that. I can let the milli part of the milliliters kind of float. So I'll go from milliliters of sodium hydroxide to millimoles of sodium hydroxide. And from there to millimoles of sulfuric acid. And from there to millimoles per milliliter of the sulfuric acid, which is my molarity. Okay, so actually executing that, I've got my 25, I'm going to say 25.0 ml of NaOH. I got a little casual here because I knew I was going to run out of space, but I want to make sure that I'm comfortable with what that molarity is, and that is that for every 1 liter of the NaOH solution, I'm going to have 0.120 moles of the NaOH. And again, I want to be very clear which concentration and volume are associated, which the respective terms, but in the interests of not running out of space, I won't overly write things down. Okay, if I stopped here, my liters would cancel and I'd have millimoles. So again, a little bit maybe new to us, but nothing wrong with that. All right, chemical reaction lets me go from 2 moles of the sodium hydroxide to 1 mole of the sulfuric acid. So at this point, again, I'd have millimoles of sulfuric acid, and then I can do some trickery. Some people don't like. I'll put a 1 here, and then I'll have my 30 ml of the H2SO4. Okay, so nothing in the numerator, just a placeholder. I'm just dividing by the volume. And remember, that's what we were saying we needed to do up here. At this point, we had moles of sulfuric acid, so we just divide by the liters, away we go. So we've got milliliters over millimoles, millimoles over milliliters, or I could convert everything to have it moles over liters. Either way, the ratio will be the same. Proven that, I've got my, again, liters canceled, my moles of sodium hydroxide cancel, my moles of sulfuric acid remain. I still have this milli out here, and I've got the milliliter here. So as long as I'm true to my prefixes and everything, I do have moles per liter, which is going to be equal to molarity. All right, when I punch all the buttons in the calculator here, I get 0.05. Again, this is going to be moles of sulfuric acid per liter, which is 0.050 molar. All right. And then lastly, maybe before I press on, I want to emphasize, and I'll come back to this, excuse me, how important this roadmap is. That if we can set all this up, then the arithmetic here really turns into a simple problem. There's less steps, the numbers are typically easier than some of those early problems we did of converting densities or converting speeds or even distances. So really embrace those roadmaps. All right, the last problem is more kind of an understanding what's going on. Maybe I call it a creative problem, but we just have to picture what's going on. And it definitely relies on definitions here. So we've got 50 mils of 0.2 molar sodium chloride, and we're going to mix that with 40 mils of 0.3 molar calcium chloride. So recognize everything's different. Volumes, I got a 50 and a 40. That'll give me approximately 90 mils. One concentration is 0.2 molar, the other concentration is 0.3 molar. Hopefully it's obvious that I can't just add those. I can't say, oh, 0.2 and 0.3, the new concentration will be 0.5. It doesn't work that way. And then just to mix things up a little, this calcium chloride has 2 chlorines for every calcium chloride. Okay, so starting a problem like this off, definitely we want to use a definition, and that will be that the concentration of chloride, and I think everybody knows this, but we want to write it down so that we're then solving that equation or solving that relationship. So the concentration of chloride is going to be the moles of chloride over the volume of solution. Okay, and again, very good idea to write that down. This is going to be the moles of chloride coming from the sodium chloride plus the moles of chloride coming from the calcium chloride. And that's going to be over the total volume. I'll just say volume total here. Okay, the volume's the easy part. It's that moles on the top we really want to be crystal clear on. Okay, so the moles of chloride from the sodium chloride, that's going to be my 50 ml times 0.2 molar, I'll put moles chloride per liter. To that, I'm going to add the 40 mils times the 0.3 molar calcium chloride, but recognize that I can either multiply by 0.3 and then multiply by 2 chlorides per calcium chloride, or since I'm running out of space, I'll do that in one step. The concentration of chloride here is double the 0.3, or 0.6. moles chloride per liter. And this is going to be over a total volume which will be 50 mLs plus 40 mLs. So taken together, that 50 times 0.2 is going to give me 10 millimoles of chloride plus 40, can't even read my writing, 40 times 0.6 is 24 millimoles of chloride, and that'll all be over 90 mils. So squeeze it out here at the end. So that 34 millimoles over 90 milliliters gives me 0.378 millimoles per milliliter, or that works out to be that in molarity. All right, so just kind of glancing back at these three problems. I don't know what the most important thing is. They kind of all are important, but being very clear what we're trying to do, define our terms. You know, if we haven't done this dozens of times, we want to be very deliberate and clear and crisp in what we're trying to do. I really find that these problems, more so than a lot of other ones, but again, everything needs to be done right, but these problems really lend themselves to these roadmaps. So focus on the roadmap. Again, you know, make sure that we know what it is we're trying to find there. You know, if we're brand new to these things, really looking at that molarity and making sure that we're clear what those units are so that the roadmap either works for us, or even more fundamentally important, seeing those units allows you to sort of pick your way through the path of what you need to do. If I just see molarity, I'm not really sure what I can connect with what. But when I see moles and liters, I make that jump of, oh, here's how I go from a volume to a number of particles. And since we've seen weeks past how we go from moles to grams, that lines up pretty well as well. All right, that's it. There's lots of problems in the book for these. Most of them, I think, tend to be kind of like this first one, and then they jump into the you know, chemical reaction type ones, which can be a little bewildering if you're not comfortable with the original steps, you know, the mole to mole stuff and the definitions of molarity. Okay, have a good night. Bye.